So in today's video, we're going to start looking into, I don't really know the proper name for this, but I'm going to be referring to it as disguised derivatives because that's kind of the only name that I saw. So essentially, a disguised derivative is just a derivative written in its limit form. And so we all, we remember the definition of the derivative in terms of a limit. We have two definitions, but the one that we're going to be referring to is this one over here. The limit as h approaches 0 of f of x plus h minus f of x over h. And kind of the intuition behind this was the fact that the derivative is the slope of the tangent line. And so with that in mind, let's actually go ahead and see how we can actually evaluate disguised derivatives. So over here we have the limit as h approaches 0 of the natural log of 2 plus h minus natural log of 2, all of that divided by h. And so the first thing that we can actually pick out from this is the actual function. So we know in this case that f of x is going to be equal to the natural log of x. And how do we know that? Well, that's because, if we look at this form over here, we have f of x plus h minus f of x. Here we have the natural log of 2 plus h minus the natural log of 2. And we don't really need to look at this 2 for the time being, because the 2, if we just ignore the 2, if we replace the 2 with an x, then here we'll end up with the natural log of x plus h minus the natural log of x, which is essentially just this form over here. And then, so we know that the function is actually the natural log of x, and so if we're going to determine the derivative, we can go ahead and actually evaluate f prime of x. We know is just 1 over x, is one of the simpler derivatives to remember. Now we actually can examine what this 2 tells us. So the 2 over here is just telling us that we're evaluating this kind of disguised derivative at x equals 2. And so this entire expression can be rewritten as just f prime of 2, right? Because we have our kind of derivative definition, and instead of an x, we have a 2. So it means that we're evaluating our derivative at x equals 2. And so in this case, if f prime of x is just 1 over x, then f prime of 2 is just going to be 1 over 2, or 1/2. And so this entire kind of limit is going to evaluate to 1/2. And then we have another example over here. And keep in mind that sometimes, we want to actually have a literal value over here. Instead, we may just have an x, and in that case, you would just rewrite this to be equal to the natural log of x if we didn't have a 2 over there. So I'm going to remove that, though. Now we're going to take a look at this one over here. The limit as h approaches 0 of tangent of h minus tangent of 0 divided by h. I'm going to leave this one up to you because, it's essentially just the same exact logic. However, the only difference here is that we don't explicitly see some sort of number written next to this h. But if you look at this over here, this tangent of 0, that just tells us that we're evaluating the derivative of this function at x equals 0. And if you work through the whole process, then you should end up with this being equal to 1. It's a very nice kind of answer right over there. Again, I'm going to leave this one up to you. You just have to be able to recognize what the function is, the x value that you're evaluating the function at, and what the derivative of the function is, given kind of this piece of information. So the limit definition can actually tell you a lot about what the function is. Although, again, in general, you're not really going to be using the limit definition very much, but I still thought it would be interesting to kind of cover the notion of a disguised derivative.